Okay, so welcome back. Today we're going to talk about overtraining. So the last model we created had an overtraining problem. So if you remember, here's a quick sketch of what we saw. We saw that the training data, the accuracy, this is our accuracy here, let's say, was going up, and our validation was kind of doing something like this, and then it kind of stalled out and did something like this. So, and of course we had a similar inverse relationship for the loss. So what we're seeing here is that as we keep training over and over and over and over again, the model is getting way more accurate with respect to the training data because it keeps looking at that data over and over again. But when we actually try to generalize it and look at pictures that it's never seen before, it starts to not perform much better and maybe even starts to perform worse. So let's look at what's actually going on here. So to do this, we're gonna look at a simple sine wave, and I'm going to explain what overfitting is just from a mathematical perspective. And this is why we can't just change the epochs to like 1,000 epochs, run it, and say, oh, the model's going to perform better. So imagine I have a sine wave that, let's say 0 is here. So this would be a sine wave, okay? So I'm going to draw the 0 line there. And the sine wave represents, let's say, the exact real model, the real life situation. But we don't know that. All we know is that we've captured some data points. So maybe we captured this data point, we captured this data point, this data point, this data point. And we're trying to, find a fit. So this would be just like in Microsoft Excel or LibreOffice Calc, if you use that, where you have, data X and Y, and then you try to fit, you might try to do a linear regression. So if we try to do a linear regression on this data, I will do that in maybe a light blue. A linear regression, we might have a line something like that. And Excel's going to say, okay, here's the equation. It's going to be, mx plus b, whatever the equation is for that line. And then it's going to give an r squared value, which is basically the error. And of course, everybody knows that, okay, if that doesn't look good, then let's try, instead of a linear function, let's try a x squared, let's try a power 2 polynomial. Not really x squared, but, polynomial of the power 2. So we change it to a polynomial power 2, and maybe we end up with something like this. And we say, okay, it's better, but it's not good. We get, of course, we'll get a different r squared value. So then we say, okay, well, let's try a cubic polynomial, and I'll do this one maybe in black. So a cubic polynomial, maybe it does something like this, okay? And that's pretty good. So the cubic polynomial matches the data shape, let's say. It matches that sine wave shape within this range pretty reasonable. So you might say, yeah, that's a pretty good fit. And then you crank it up. Let's say you go all the way up to like a power, 7. You might, or whatever the limit is in Excel. So let me erase this because it's getting kind of complicated. Well, what'll end up happening is eventually when you have X number of variables and X number of, an X polynomial, you can get it to fit 100%. So again, if this was our sine wave, and we used a really high order polynomial, for example, and these are, I'll just draw again, these are our data points, let's say, something like that. Well, we could find a function, I'll draw this in green, we could find a very high order polynomial that'll fit all those exactly. And it might look like this, though. It might look like this. But guess what? That function will pass through every one of those points with 100% accuracy. So it's possible. So if you were to look at the r squared, it might be 1.0 because it's able to fit that function to exactly all of those 4 points. But when we look at that function, it actually doesn't match the real function at all. So this is an example of overfitting. So this is why we use validation to check. So if I was to draw this function, and how about this in light blue, I will draw that third order polynomial, for example. So it's not going to be exactly on the red line, but it's going to be closer. So if we were to draw the r squared value of the blue one, it might only be, let's say, 0.95, and the green one is a 1.0. It's able to exactly pass through all of those points. But when we calculate the error and we integrate the error, this pink region, let's say, is the error between the blue line and the red line. We see that the overall accumulated error is quite low for this blue function. And in yellow, if I were to draw the error between our green function and our red function, which is the sine wave, you'll see that we have this huge amount of error. So what this would represent is again, the r squared one, this is kind of like the training data. So we're able to fit the training data with 100% accuracy. But as soon as we throw any new data at it, so let me clean this up a little bit. So again, here's my function, here's my data points. When I measure against my training data, I'm able to exactly hit all of these points with 100% accuracy. But as soon as I throw in a new data point, so let's say this magenta point here is a new data point, and I test, if my function's doing something like this, well, guess what? The error between my function and this prediction is extremely large, and that's what overtraining essentially does. So essentially, that's the problem with overfitting, is we're able to exactly fit our training data with 100% accuracy, even. But as soon as we throw anything else to try to generalize the model, we end up with extremely large error. And that's what was happening to our model that we were training in the last video. As we kept training it, you saw that we got more and more accurate with respect to our training data, but our validation data started to flatten out, and it was probably going to start to get worse. So that is overfitting in a nutshell.